It happens all the time, right? Your phone unlocks just by looking at it. Your photo app knows exactly who's in the picture and tags your friends automatically. But have you ever stopped to think about how that actually works? How does a computer, just a bunch of code, see a face? It really feels like magic, but the secret? Well, it's not about what the computer sees, it's all about how it thinks.
And right there, that's the whole secret. Get this. To a computer, your face isn't a face. It's not eyes, a nose, a mouth. It's just a giant grid of numbers, an ocean of data. And that single idea, it changes everything. It's literally the foundation for everything we're going to talk about today.
So, in this explainer, we're going to pull back the curtain on computer vision. We're going to figure out what that code behind sight really is, how we translate the rich, visual world into a language that a machine can actually understand.
All right, so first things first, we've got to learn this new language. If a computer doesn't see a picture like we do, what does it see? Well, it sees pixels. And guess what? Pixels speak in numbers.
And that's really it. It's that simple, but it's also kind of profound when you think about it. A black and white photo? To a computer, it's just a spreadsheet full of numbers. A color photo? Same idea, but now you've got 3 spreadsheets stacked on top of each other. One for red, one for green, and one for blue. So every single thing you do to an image, whether it's making it brighter or finding the edge of an object, it's just math. Just operations on that grid of numbers.
Okay, so if we're going to work with all these numbers, we need the right tools, right? We need a mathematical toolkit. Think of it this way. Linear algebra, that's our pattern finder. It helps us see the structure in the data. Geometry, that's for moving things around, for transforming the image. And probability and statistics, oh, that's a big one. That helps the machine make a smart guess when things are messy or unclear, which, let's be honest, in the real world, they almost always are.
But wait, that brings up a pretty big question, doesn't it? A single high-res photo can have millions of pixels. That's millions of numbers. Most of that is just noise. It's the boring wall behind you or a patch of grass. So how on earth does the computer know to focus on the important stuff, like the eyes and the nose, instead of all that background clutter?
Well, the answer is actually a really powerful idea from statistics. It's called variance. The computer basically learns to pay attention to the places where things are changing the most.
Okay, think about it like this. Imagine a photo with a big, clear blue sky. The pixel values for that sky are all going to be super similar, right? That's low variance. Not much is changing. But what about the edge of a building against that sky? Bam, you get a huge change in pixel values. That's high variance. The computer figures out pretty quickly that high variance, that's where the interesting stuff is happening.
And this idea right here, it gets at a really fundamental truth about images. Even though a photo is technically made up of millions of data points, all those pixels, the important information, the face, the car, the cat, it can usually be described in a much, much simpler way. It's like you're trying to find a simple trail through a huge, dense forest. So the question is, how do we find that simple path? How do we cut through all the noise? Well, thankfully, we have a tool designed to do exactly that. And it's kind of the hero of our story today. Let me introduce you to Principal Component Analysis, or as we'll call it, PCA.
So what PCA does is actually pretty clever. It's an algorithm that looks at all that messy data and asks one simple question. In which direction does the data change the most? It finds that direction of maximum variance, draws a line through it, and calls that principal component 1. Then, it looks for the next most important direction, and so on. It's basically a methodical way to take all that complexity and just boil it down to its most essential parts.
So that first component, PC1, it captures the single biggest, most dominant pattern in the data. For example, if you feed it a bunch of photos of faces, maybe PC1 represents the general direction the light is coming from. Then, PC2 finds the next biggest pattern that's totally separate from the first one. Maybe that's the difference between people wearing glasses and people who aren't. Each component just keeps adding another layer of detail, always in order of importance.
But, and this is absolutely crucial, we have to be really clear about what PCA is actually doing, and maybe even more importantly, what it isn't doing. See, PCA is incredibly powerful, but it is not intelligent.
This really lays it all out. What PCA does is fantastic for prepping data. It simplifies things, it gets rid of noise, it cuts out redundant information. But look at what it doesn't do. It doesn't classify anything. It has zero idea what a face even is. It can't understand labels like cat or dog. All it does is find patterns in the numbers.
In this quote, this is probably the single most important thing to remember about PCA. It optimizes for variance, not for usefulness. It's programmed to find where the numbers change the most, but it has no clue if that change is actually useful for what you're trying to do. You know, the biggest change in your dataset might be the lighting conditions, when all you really care about is figuring out who is in the photo.
And that's the key right there. The meaning. That comes from us. Calling one pattern lighting and another one glasses, that's a human interpretation. The machine just finds the pattern. We're the ones who give it meaning. PCA is like a brilliant assistant that's amazing at finding patterns, but it needs us to tell it what they mean.
Okay, so let's bring this all back around. We've talked about matrices, variance, PCA. How does all this foundational math stuff actually connect to the apps and the tech we use every single day?
Well, the connection is about as direct as it gets. Those super complex convolutional neural networks, the CNNs that are the backbone of modern image recognition, they're built on these exact principles, like dot products. Those powerful editing tools and software like OpenCV, it's all matrix operations under the hood. Even the crazy fast, real-time object detectors like YOLO are using this kind of geometric reasoning. So the math we've been talking about, it's not just some abstract theory. It is the literal language that all these modern systems speak.
And here's the bottom line. The real world and the pictures we take of it, it has structure. It's not just a bunch of random noise. And because that structure exists, we can use amazing tools like PCA to find a much simpler, cleaner way to describe it. Honestly, that's the core reason computer vision is even possible in the first place.
All right, we're almost at the end. So if there is just one thing you take away from all of this, let it be this.
Look, pretty much anyone can import a code library and run a model these days. But what happens when it goes wrong? When it gives you a bizarre result you can't explain? That's when understanding the math, knowing what's going on under the hood, becomes your superpower. It's what lets you debug the problem, explain the outcome, and, most importantly, trust the tool you're using. It's what makes the difference between just being a user and becoming a real innovator.
And that leaves us with one last question to chew on. We've seen that a machine can be incredibly good at finding mathematical patterns in data. But if the machine only sees the numbers in the patterns, and not the actual faces, or cats, or cars, then who teaches it what our world actually looks like? Who connects the patterns to their real-world meaning? And that question, well, that takes us beyond the math and right into the very heart of modern AI.